Hello students, this is part 2 of chapter 2, and we're going to get into atomic symbols, isotopes, and move into moles and working with Avogadro's number. So just make sure you have a calculator and paper and pencil. So the last time I showed you the atom, made up of protons and neutrons here in the nucleus, and most of the space is composed of the electrons. Let's talk a little bit about what they weigh and their charge. So protons and neutrons contribute the mass. We say for each of them, they weigh one atomic mass unit. They actually weigh something specific in grams, but it's a little tedious to always use these sort of numbers. You know that the electron weighs something teeny tiny as well, but relative to the proton and neutron, it's negligible. So we say the electron weighs 0. In terms of the charge, the proton is a +1 charge, and the electron is a -1 charge. There are real charges, as you saw in the first video, but it's simpler to just focus on +1, -1. The neutron is neutral and has a 0 charge. It's very important to really understand that the charge of a particle comes from the balance or imbalance of protons and electrons. If, for example, I have a normal atom, say 6 protons, 6 electrons, it's neutral. If I pull out one or more electrons, overall what's left is something positive. That leads us to ions, which we get into later. Did you ever wonder, is there anything smaller than a proton, neutron, and an electron? Maybe you have, maybe you've seen this in a physics class. I just, for fun, wanted to give you the bigger picture. Here's our atom. Here is the nucleus with protons and neutrons. And the protons and neutrons, they're not the most basic you can get. They're not what are called elementary particles. They're actually made up of something smaller called quarks. And in this case, these are up and down quarks. You don't need to know that, but I found it interesting. The other thing is that electrons, those are elementary particles. There's nothing making up an electron. A lot of times we will just be writing out a type of element or ion and use what's called its atomic symbol. So the element symbol will be given in a big letter, here X. So for sodium, it'd be a big N and a little a. The mass number up in the upper left is important because we have what's called isotopes of different mass because they have different numbers of neutrons. So that's in the upper left, the mass number. The atomic number, Z number, I will refer to Z a lot. So the Z number specifically is the number of protons. I want to tell you that this atomic symbol is arranged with mass in the upper left, atomic number in the lower left. Sometimes you don't see the atomic number because you know the number of protons because it has to be a specific number for each element. So sometimes that's missing. But let me just tell you, do not be fooled by your periodic table. Sometimes they put the big atomic number on the top. So I just want to mention that. The mass number is the number of protons plus neutrons. Here's an example of just a simplistic view of a carbon-12 atom. A carbon has 6 protons. So in a normal case, it'll have 6 neutrons and electrons as well, as you can see here. So we write 6 in the lower left and 12 in the upper left for 6 plus 6. For oxygen, atomic number 8, it has 8 protons, neutrons, electrons in a normal situation. And so we can write 16 in the upper left. That mass number differs when you have different numbers of neutrons. We call those other versions of the atom isotopes. So carbon there are 3 different isotopes of carbon. There's carbon 12, 13, and 14. This is basically dependent on how it was kind of constructed at the start of the universe. And it can be different on different planets. So carbon 12 is what we've discussed, 6 protons and 6 neutrons. This makes up about 99% of the carbon atoms on Earth. So for example, if I took a whole bag of carbon and I picked out an atom at a time. 99% of the time I would come up with carbon 12. 1% of the time I would come up with carbon 13. 6 protons and 7 neutrons, and then even much less carbon 14. This is actually radioactive. You can use this in radioactive dating. This has 8 neutrons. So what's interesting is, have you ever looked at the periodic table and seen that other number there? That's the mass number. You don't see exactly 12.000 for pure carbon 12. You see something else. You see 12.011. Why is that? It's because the mass on the periodic table reflects a blend of all these, a weighted average where 99% weighs 12, but 1% weighs 13, and a little less or less than 0.1% weighs 14. So it's close to 12, but a little heavier because of the other isotopes. So here's an example. Say I have gallium, 2 naturally occurring isotopes. Gallium has a mass of almost 69, 68.9, and gallium-71 has a mass of 70.9. The abundance on Earth is 60% of gallium is the lower mass gallium-69. So my question to you is, just in general terms, don't use your calculator here, what can you say about the atomic mass of gallium? Meaning, what mass number would you expect on the periodic table, roughly? Would you expect 69? Would you expect 71? Would you expect something exactly in between, 70? You would actually expect something in between, but closer to the one that there's a higher abundance of. So it would be closer to a mass of 69. You can look on the periodic table and see what that is. A really interesting use of isotopes, and there are many, is one that's relevant to athletes. So many of you might have heard of or watched the Tour de France. Basically, these are cyclists. Lance Armstrong was a major athlete in this event. There was also a disgraced cyclist, Floyd Landis, and he was basically accused of doping, and it was proven through the use of isotopes. So basically, the athletes, they have to pee in a cup. They analyze the urine, and what they found in Floyd Landis's urine was that there was just simply an extremely high level of testosterone. So that in itself, could that prove that someone's doping? Not necessarily, and no, it really shouldn't, because we all have different variations in terms of our body function. But what they did do was they looked at the testosterone molecule, and each point here is a carbon that's not drawn out with hydrogens attached. You don't need to know that, but in case you're interested, they looked at the isotopic ratio of Floyd Landis's testosterone. The reason is, if he bought some pharmaceutical grade, that would be different than the one that the body produces. The pharmaceutical testosterone has more of the C13 isotope than the natural one that's normally found in people's body. So they did find that he had elevated C13 to 12 ratio, and that's how they caught him for doping. Okay, we are moving on to the mole and doing a few calculations here. I already talked to you about the mass. So the mass of one atom of sodium is 22.99. You can estimate the mass of sodium. Sodium has an atomic number of 11. Look at your periodic table. That means it has 11 protons, 11 neutrons. It should be around 22. But why is it higher than that? Hopefully you came up with the fact that there must be some sort of higher mass isotope, and there is. The most abundant one is sodium 23. So all combined, the weighted average, you get 22.99. So if I'm just talking about a single individual atom of sodium, I'm going to say that mass is 22.99 AMU, atomic mass units. But in the lab, we don't weigh out atomic mass units. We weigh on a balance in grams. So scientists have come up with a clever way to work with this. And basically, we created a unit called the mole that for a mole of a substance, it will have that mass in grams. So one sodium weighs 22.99 atomic mass units, but 1 mole of sodium is going to weigh 22.99 grams. So scientists designed it that way so we can easily read off the periodic table and come up with something called molar mass, 22.99 grams of sodium per 1 mole of sodium. So you'll find that you'll be able to use this as a conversion factor. Here's an example. How many moles are in 68 grams of sodium? And the mole use is very important in reactivity. Later, we're going to use equations, and it's the only way you can work with reactants and products is through moles using an equation. So this is really critical and a very common conversion you'll do. Start with your 68 grams of sodium. You need to go to moles. The only way to do that is put grams in the denominator and moles in the numerator. And I can do that directly using molar mass. Using the molar mass of sodium, keep the 22.99 with the grams, and it's always 1 mole for molar mass. Crunch the numbers, you get this. I tracked 4 sig figs, so I put a line, but I carried out at least 1, and then I gave my final answer below. Recall, this is molar mass. In this case, I put the grams on the bottom and moles on the top to cancel out grams. If I did the inverse, I would have gotten grams squared over moles, which just doesn't work. So canceling out the units, double check to make sure you did that correct. Okay, now let's get to atoms, the number of atoms. Sometimes we are interested in the actual number of individual atoms in an element, or if I'm talking about a molecule, the number of molecules, or even ions. So let's take 1 mole, which is 12.00 grams of pure carbon 12. How many atoms of carbon are in there? You may already know the answer to this. 6.022 times 10 to the 23. That's a number ingrained in my memory. This is Avogadro's number. This is a number that comes out from what scientists created the mole and then counting the number of carbon atoms in there. There are a variety of ways that you can do that, using X-ray, another way with charge. This number, it's just a number. Think of it as just representing 6.022 times 10 to the 23 things. That could be atoms of carbon, that could be ions, say OH hydroxide ions, molecules, N2 molecules, bunnies, little kitty cats, whatever. It's a number. Let's use this. How many atoms are in 0.45 moles of cobalt? Start with what you're given, 0.45 moles of cobalt. If you don't like this just freestanding here, put a line and a 1 under it. And then I want to go from moles to atoms. The only way you can do that is Avogadro's. And it's always 1 mole. I put that in the bottom so the moles cancel. And then I put the atoms on the top and I put Avogadro's number. Why the atoms and not molecules? Because cobalt exists by itself. Cobalt, it's not bound to a second cobalt like the halogens are, like F2, Cl2, or N2O2, or H2. Those would be molecules. Go ahead and crunch your numbers. Try this in your calculator, and this goes out to 2 sig figs. So notice I carried out the digits, but I put a line to represent, I'm just gonna cut it off after these first 2. So my final answer, I don't round up, because it's 0, I get 2.7 times 10 to the 23 cobalt atoms. Again, to do that conversion, that's Avogadro's number, always 1 mole. This is our last slide. I want you guys to pause this and answer these questions. And For this bottom one, you need to know the mass of H2. There are 2 H's in that, so you need the mass of 2 H's. Okay, pause that and I'll go over it. So the first says write the atomic symbol for an element with 24 protons and 28 neutrons. The protons identify the element. So you go to the periodic table, you go to the big atomic number, and it may be on the top, it may be on the left, and you find 24, it's for chromium, and you put that in the lower left. And then the mass number is the sum of these two, 52. The second one is how many H2 or hydrogen molecules are in a 5.55 gram sample of H2. Start with the 5.55 grams, and you want to go to molecules. I can't go there directly from grams. I have to use moles as a bridge. So I got to go grams to moles first, and then I'll go moles to molecules. Grams to moles, I put grams in the denominator to cancel, moles in the top, and then I'll put my numbers in. H2, one H is 1.008, so 2 of them is 2.016 grams, and it's always 1 mole for molar mass. So then these grams will cancel. And then I move on. I want to go moles to molecules. So I put the molecules on the top, moles on the bottom. And what I do is I put 1 mole, because that's Avogadro's, always 1 mole, and Avogadro's number with the molecules part. Again, it's just a number. And if you're still unclear, do I use atoms, molecules, ions, whatever? Look at what you're talking about. I'm talking about H2. H2 is a diatomic. 2 atoms are bound, so we just call those molecules. If it was just H alone, if I asked you how many H atoms are in something, then you would write H atoms. Practice, crunch the numbers. Notice everything cancels. You're left with the number of molecules. Out to 3 sig figs, you get 1.66 times 10 to the 24. Okay, I'm going to end here, and we'll continue more later.